Let's be real. When you're working with data, speed is everything. But what happens when a really fundamental data structure, the search tree, gets all bent out of shape and slows to a crawl? Well, today, we are demystifying its super elegant solution, the red-black tree. We're going to break down exactly how it guarantees you get high performance every single time.
So let's kick things off with that very problem. You see, a standard binary search tree is fantastic in theory. But if you give it the wrong kind of data, it can become incredibly inefficient. It basically just throws all of its advantages right out the window, and everything grinds to a halt.
All right, here's our game plan. We'll start with the problem itself, the unbalanced tree. Then, we'll look at the promise a red-black tree makes. After that, we'll dig into the 5 core rules that make it all work, see how it actually restores its own balance, and finally, celebrate that sweet, sweet O-login performance payoff.
Okay, let's dive right into part 1, the unbalanced tree problem. Why exactly does a simple, totally well-intentioned search tree so often fall flat?
Here's the heart of the issue. Imagine you're inserting data that's already sorted, like the numbers 1, then 2, then 3, and so on. The tree doesn't grow out wide and bushy like it's supposed to. Instead, you get this long, skinny, degenerate chain. It basically becomes a glorified linked list.
And that is the core problem. The whole point of a tree is to divide and conquer, to be fast. But here, you have to check every single node one by one. Your search time totally degrades to O of n. That means the search time grows in a straight line with the number of items. Double the data, you've just doubled your wait time. It's painfully slow.
So how do we stop this lazy, chain-like structure from ever forming? Well, let's look at the red-black tree's promise to keep itself, and I love this phrase, always balanced enough.
So what is a red-black tree really? Well, at its heart, it's just a normal binary search tree, but with one simple, absolutely brilliant addition. Each node has an extra property, a color, that's either red or black. It's this simple color that lets the tree police its own shape.
And here's the magic. By enforcing a very specific set of rules based on those colors, the tree makes a guarantee. Its longest path from the top to the very bottom will never be more than twice as long as its shortest path. This promise means it can never get too tall and skinny, locking in that incredible efficiency.
So, what is this secret sauce? How do a few simple, non-negotiable laws create such a powerful performance guarantee? Let's find out.
These are the 5 commandments, the rules that every single red-black tree has to live by no matter what. Now, they're all important, but pay close attention to number 4, no 2 red nodes in a row. And number 5, every path has the same number of black nodes. Those 2 are the real heavy lifters for keeping things balanced.
You know, to make this a little more concrete, think of it like a bookshelf. The black nodes, those are the strong structural supports. Rule 4 is like saying you never stack 2 flimsy decorative red brackets right on top of each other. And Rule 5 means that no matter where you start on a shelf, you always pass the same number of black supports to reach the floor. It's a simple idea that keeps the whole shelf from ever tilting too far.
Okay, you might be thinking, if these rules are so strict, what happens when we add or remove a node? How does it stay legal? Well, it uses 2 simple but really powerful tools, recoloring and rotations. The tree's first line of defense is just a quick paint job, changing nodes from red to black or black to red. It's a fast and easy fix. But when just changing colors isn't enough to solve a rule violation, the tree pulls out its other trick, a really clever structural maneuver called a rotation. So let's imagine we've just inserted a new node and, we have a problem. Look at this little section of the tree. We've got 2 red nodes in a row. That is a big no-no. It violates rule number 4. We've got to fix it. So to fix this, the tree performs what's called a left rotation. Just watch this little section here. It's a very simple, very local pivot that just rearranges the parent-child relationship without messing up the rest of the tree. And boom, just like that. See what happened? Y is now the parent, and X is its child. The tree is still perfectly sorted, but that little pivot adjusted the local structure. It broke up that illegal red-red pair, and balance is restored. It's this beautiful dance of recoloring and rotating that keeps the tree in perfect health. So, we have these strict rules, and we have these clever fixes. What's the ultimate payoff for all this self-management? Why does any of this really matter? Let's get to the final section. This right here, O log n, this is the hero of our story. It stands for logarithmic time, and it is an incredibly powerful concept. It means that even if your data grows from 1,000,000 items to 1,000,000,000 items, the time it takes to find something barely even budges. It is the absolute gold standard for high-performance searching, and red-black trees guarantee it.
Just take a look at this. Searching, inserting, deleting, it doesn't matter what you're doing. Average case, worst case, it's always O log n. There's no catastrophic O of n scenario like we saw with the simple binary search tree. That incredible reliability is why they're so valuable.
Now, red-black trees aren't the only game in town. You might have heard of AVL trees. And when you compare them, you see this classic engineering trade-off. AVL trees are stricter. They keep themselves almost perfectly balanced. That makes searching them just a tiny bit faster. But that perfection comes at a cost. They have to do more rotations when you add or delete things. So for applications with tons of inserts and deletes, red-black trees are often the winner.
And believe me, this isn't some dusty concept from a textbook. Red-black trees are the unsung heroes working behind the scenes in systems you use every single day. We're talking about the standard libraries in C++ and Java, the schedulers in the Linux kernel, memory allocators, the list goes on. They're everywhere.
So I think the big idea here is that a few simple local rules can create a system that is incredibly complex, efficient, and reliable on a global scale. It's a concept that goes way beyond just data structures. And it makes you wonder, doesn't it? What other complex problem, maybe in technology or even in society, could be elegantly solved with just a few simple, clever rules?